I mentioned earlier in this chapter that although the left inverse, so this solution here, is the mathematically appropriate way to implement least squares, it is not necessarily the best way to implement it in practice, in part because of this inverse here. So inverting this matrix can cause some numerical inaccuracies or instabilities. And there's some other reasons as well that I mentioned in the chapter. And then I discussed several alternatives for implementing least squares in a more computationally sensitive way, including QR decomposition. You can also do it with LU decomposition, Gauss-Jordan elimination, and so on. There's several more numerically stable methods, and that is also a topic for the next chapter. But the general purpose of this exercise here, exercise 3, is to explore different techniques, different algorithms for obtaining the coefficients, the beta values. So what you want to do here is solve the least squares problem, still working with this happiness and online courses taken data set that we're using in this chapter. So the three methods you want to use are the left inverse, where you explicitly implement this formula, QR decomposition, which I explained earlier in the book, and Gauss-Jordan elimination on matrix R augmented with vector Q transpose Y. Okay, now I'm going to briefly scroll back up to page 187 here. I'm not going to talk about this in a lot of detail because it's in the book, but just to remind you, to show you what this looks like. So here we have the equation x times beta equals y. Y is the data vector, x is the design matrix, and beta is the vector of unknown coefficients, and this is what we want to solve for. So the QR solution is to replace x with QR, so the QR decomposition of the design matrix, and then it's pretty straightforward to isolate beta, and you don't have to invert Q. You do have to invert R, but as I mentioned in the previous chapter, in writing and also in these exercise videos, this is more numerically stable because it's triangular, it has lots of zeros, and so on. So you implement these three different methods in Python, and then print out the betas from all three of these methods. And you can see that they are the same. Here's this one, and then the next one is on the next page. My apologies for the slightly poorly placed page break here. But you can see that the beta coefficients are all the same, no matter how you do the analysis, no matter what algorithm you use to implement least squares. And then finally print out these resulting matrices from QR. So we have matrix R augmented with the vector Q transpose Y, so that you see here. And then we have the RF, so the reduced row echelon form of this concatenated or augmented matrix, basically. So we get the identity matrix over here and the beta values over here, and this is the solution through Gauss-Jordan elimination. Okay, so now I will switch to Python and show you how I solve this problem. It's mostly straightforward. There's a couple of tricks here and there about working with Python NumPy arrays. I have code here, it's commented, but if you uncomment this code, then basically you'll be running this on random numbers data with the random numbers design matrix. That's just to continue exploring these. You can see here I'm varying the size of the design matrix. But I'm going to, for the purposes of this video, I will continue using the data that we created earlier. So the number of courses and the happiness score and the design matrix, which I'm just recreating here in case you are generating new data here. Okay, so here we have one way of calculating the betas. This should be familiar to you by now. This is the left inverse of the design matrix, multiplying the dependent variable, the vector y, which here I call happiness. So here we get beta 2. Here I'm implementing this through QR decomposition. So we take QR decomposition of the design matrix, and then we have to invert R and multiply that by Q transpose Y. Okay, so that's beta 2. And now we get to beta 3. And how do we get beta 3? So I'm going to read this coming from the bottom up. We get this from the last column of this matrix R og R. So R og R, kind of fun to say, is the reduced row echelon form of this matrix, which is the R matrix from QR decomposition, and then augmented on top of that is Q transpose times Y. And now, again, this is one of these kind of annoying things in NumPy that if you have an array, a vector that doesn't have a orientation, it's one-dimensional. It doesn't have it's not a column vector or a row vector. Sometimes that's fine, and you don't need it to have an orientation. And sometimes you do need it to have an orientation. In this case, it needs to have an orientation in order to stack or augment the vector onto the matrix. And so that's why I'm using this reshape function here. Okay, so getting back here. So here we take the reduced row echelon form of this augmented or concatenated matrix. Now, the thing is that NumPy doesn't have a routine for computing the reduced row echelon form, so I can transform this NumPy array into a SymPy matrix. All this stuff gets really, in my mind, needlessly complicated, but this is how it is in Python. Okay, so I hope that all makes sense. Basically, we are computing the beta values, so these coefficients, in 3 different ways using 3 different algorithms. And the point of all of this code is you can see that although we're, kind of playing around with the linear algebra, we end up with exactly the same results no matter where we start from. Now, this shouldn't be so surprising because theoretically, these are all the same method. We're just kind of moving things around and taking slightly different approaches. It turns out that you're not guaranteed to get exactly the same solution in all of these cases, and you'll see that in the exercises in, I think it's the next chapter, where in fact these different methods give you different results because some of them are more numerically stable than others. When you are working with simple problems, so toy examples or relatively small data sets, then you really get a lot of wiggle room. You can do whatever method you want and it's always going to come out. All right, so then here, this code here, the purpose is just to make sure that you are familiar with working with and looking at and thinking about the QR decomposition of the design matrix. So here I've printed out matrix R. Of course, it's upper triangular. There's a 0 here. Here we have augmented R with Q transpose Y. And then here we have the reduced row echelon form of this augmented matrix. So the R part of this matrix turns into the identity matrix, and the augmented vector here turns into the betas. These are the solutions that we are looking for.